In Chapter 4, Notes E, we're going to look at some of the big network covalent bonds and how that affects some of their physical properties. I want to start by comparing 4 different allotropes of carbon. So first, to define the term allotrope, it basically means it's the different crystal structure that could form out of the same basic element. So carbon can bond in 4 different ways with itself in order to form these 4 different structures. Those are the allotropes of carbon. The first version I want to look at is something you should be familiar with, graphite, which is used as the lead in some pencils. Graphite is sp2 hybridized as it is bonded with 3 other carbon atoms. The sp2 hybridized carbon atoms will form hexagons, but what's interesting is the hexagons will layer on top of each other. And then, of course, you would have interactions in between the 2 layers. So that's going to lead to some interesting chemical properties. It is a good conductor this way, as it creates a large network for the electrons to be delocalized and flow between. And it does have a higher density of 2.26 grams per cubic centimeter. The appearance for graphite, as you may be familiar with if you look at your pencil, if you're taking notes with pencils, it's not a very shiny or lustrous material. It's just kind of a dull gray, and it is solid at room temperature. Next up we have graphene, not to be confused with graphite. Although it is also sp2 hybridized and has a very similar density, the difference here is that it is not a stacked plane of hexagons. It is just one sheet of hexagons. It actually is almost impossible to see. It is almost completely transparent because it's only one atom thick, only having one layer of those hexagon shapes. It is a very good conductor of both electricity and especially of heat. So it even has a better thermoconductivity than diamond, the next shape that we're going to look at. So because it's such a good conductor, it's really good for things like solar panels. It's what makes your touch screens work on your phone. Very good for helping out with electrical device, being able to conduct the electricity so well. Now on to diamond. So yes, the pencil lead that you're writing with and the diamonds that you're familiar with, these very expensive crystals made from the same exact atom, but it does have a different crystal structure. With a diamond, you're going to get sp3 hybridization. It's going to be bonded actually to 4 carbon atoms instead of 3. So instead of having this hexagonal structure, it's actually attaching in 4 directions, more of a tetrahedral orientation for each atom. It has a much higher density of 3.51 grams per cubic centimeter. Actually, it is the hardest known natural substance. It is not a conductor, though, because all 4 atoms are involved in bonds, degenerate bonds, and so that means that all of those electrons are localized. Without any delocalized electrons, you're not going to get any movable electrons, no flow, and so it's not going to be very good at conducting, more of an insulator. The appearance you're probably familiar with, that very shiny, lustrous crystal, more of that white-looking crystal than a gray color. And it, of course, is used in jewelry, more of a visual showpiece, but you may not have known it's also really good for tools and machinery. Because it is the hardest known substance, that makes it very good at cutting things. It can cut through glass. So you have these tools that may be diamond tipped or diamond encrusted, and that's to help with them being hard enough to cut through other things that are really hard. Our last carbon allotrope is called Buckminsterfullerene, and it has a very interesting shape. It almost looks like a soccer ball. Although it has a pretty complicated name, it's often called a buckyball for short, and that's named after an architect who made a very famous structure, seen here. So we call the structure of this Buckminsterfullerene a buckyball for short. You may have noticed that the hexagons are back. So this is also sp2 hybridized, just like the graphite and graphene were. Anytime you have those hexagons where it's bonded to the 3 carbon atoms, you're going to get that sp2 hybridization. But this crystal structure is much more complicated and spread out. So the density is lowest of all of the 4, 1.72 grams per cubic centimeter. It's going to be a semiconductor. Not an excellent conductor, but not as locked in as the diamond was, but you can see that this network is a little bit more involved, and so you have less electron mobility than you would from the good conductors like graphite and graphene were. It is actually yellow in color and is a crystal structure, crystal solid. Some of its more well-known uses are to actually make something called a superconductor, which, as you might expect, is really good at conducting, but in order to do that it has to react with potassium, because notice by itself it was only a semiconductor. And then another really common use is to use it as a catalyst for other reactions. Another element that is well known to make these network covalent bonds is silicon. It's also in group 4, located right under carbon in the periodic table, which means it has 4 valence electrons. So it would like to have the tetrahedral arrangement, bonding to 4 atoms in degenerate orbitals, and that's going to give it a very lattice-like structure. So the structure is going to look a little bit more like the diamond allotrope of carbon. One of the most commonly used form of a silicon network actually is when the silicon is involved with oxygens. Silicon dioxide would be formed. This is going to create what's known as a silica gel or quartz. It is also a giant covalent structure. You'll use silica gel in labs like thin layer chromatography, and you may be familiar with quartz. It also can be under high pressure turned into glass, like the glass that we would have in our windows. So a very common, very important compound. It is also tetrahedrally shaped, but the bonds are actually between the silicon and the oxygen. So you can see in the picture to the right, there's an alternation, like rotating back and forth between silicon, oxygen as you go around the structure. So every silicon atom is going to be attached to 4 oxygen atoms. So if you look at what I just circled, that black dot in the middle would be the silicon atom, and then the 4 red dots around it would be the 4 oxygen atoms. But every oxygen atom is only attached to 2 silicon atoms. So now if you look at what's circled, the red would be the silicon in the middle, and it's attached to the 2 black dots, being the silicon atoms. This entire diagram to the right is only one subsection of the network. It would go on and attach to more oxygen and more silicon atoms in the same exact ratio, where every silicon has 4 oxygen atoms and every oxygen has 2 silicon atoms. This network would just propagate as it got bigger and bigger. Let's move on to metallic bonding. In metallic bonding, the valence electrons of each metal atom become completely detached, and so then you have a sea of delocalized electrons. Now the metal nucleus has a positive charge, and the electrons are floating around the outside of the metal nucleus. This is often called the electron sea model, where all of the valence electrons as a whole are free to flow throughout the metal. So where exactly is the metallic bond? The metallic bond is defined as the attraction between the neighboring positive ions and the delocalized electrons between them. So as we have 2 electrons that are between the 2 positive nuclei, that would constitute one metallic bond. This is obviously a system in flux, where the electrons would be different from one moment to another, but at any given time, there should be some form of electrons in between the nuclei, and that's what holds the metals together in a metallic bond. Metallic bonding gives rise to a couple of interesting physical properties for metals. For one, metals are malleable, meaning they can be bent and reshaped. They are bendable. The next is that they are ductile, meaning they can be drawn out into a wire, which is very good for things like Fios internet. The copper can be drawn out into a wire shape and used to wire houses. Being malleable or ductile both require some kind of flexibility in their form. And this is only possible because that metallic bonding is in flux. And so the ions, or the positive nuclei, I should say, can then slide over each other without breaking, because they still have other electrons that they can be held together with. It's all in flux. It's important to point out that the ability to be malleable and ductile is more applicable when the metal is pure, when you have pure aluminum atoms interacting with other aluminum atoms. Introducing impurities or even just mixing two different metals together to create something called an alloy would deviate from this metal nature. So it would make it less bendable or less ductile, less malleable, less ductile. So that's going to create a harder substance, which can also be a good thing. You may be familiar with more hard metals like steel. These are alloys, and so they won't be as malleable or ductile. Now let's talk about how the different types of bonding affect a substance's melting or boiling point. We know that a substance's intermolecular forces are what hold together different atoms to create liquids and solids. Gases would have no intermolecular forces. So we can measure the strength of the intermolecular forces by looking at the phase changes. And boiling is actually a better indication than melting point, because in a boiling point, you've now destroyed all of the intermolecular forces in order to create an ideal gas. Melting point would give you a similar indication, but to a lesser degree, because liquids do still have some intermolecular forces. So as we move on, I'm going to focus mostly on boiling point. I do want to take a second to talk a little bit about the melting point setup for determining the melting point. We're doing this lab on a gizmos this week. Usually it is a skills lab for IB, something you're supposed to be able to physically set up. So I want to make sure we talk about the setup a little bit. There is a new piece of glassware used called a thiel tube, and it looks a little bit like a test tube in one section of it, but it is important that it has a little arm that goes out. This allows for convection to go through the water to carry the heat. You don't want to apply the heat directly to where the substance is. Notice that the flame is a little offset. You're applying the heat over on the arm portion of the glass and then allowing convection to carry the heat over to where you would have the sample inside the tube. So here we have a close-up of the setup inside the thiel tube. The thermometer is going to be attached to a capillary tube. We usually use a rubber band actually to tie these two things together. You want to make sure that the tip of your thermometer is lined up with where your substance is so that you can take the temperature of the area where the substance is to get the temperature of what's happening to the substance. We're going to load that substance in something called a capillary tube, which is just a very thin tube that is open so that you can then load the substance in. You're going to want to grind it first with something called a mortar and pestle, and then you touch your capillary tube to the powder and tap it down, and you do that over and over again until you can get enough to keep the height with the thermometer sensor. Once you've got that lined up, you're going to bind it with the rubber band, and then stick that down into your thiel tube. One thing that they don't show in this picture is you would then need a ring stand set up with all the clamps to hold this in place, which is why it's a little complicated to set up and more of a skills lab. But at least now you kind of can picture the lab and see how you would set it up, and especially understand the importance of our new glassware, the thiel tube. Impurities also affect the melting point or the boiling point, as they're also going to interfere with the bonding in between the atoms, and so as it's affecting the intermolecular forces, it's going to then affect the melting point. So adding something to a substance can actually lower its melting point. We talked about this with the colligative properties of water. When we had salt water versus sugar water, we had a greater effect with the salt. So the more impurities you're adding and the more particles that breaks down into, the more you're going to depress the freezing point or melting point. Thinking back to the bonding from carbon and silicon, those giant networks were covalent macromolecules or large molecule structures. Those are going to have very high melting and boiling points because they're going to have very strong intermolecular attractions. Ionic compounds and metals with these free-flowing electrons and the lattice structures for ionic compounds, those are also going to have relatively high melting and boiling points because you do have those interactions between the positive and negative particles. When we get down to an intermolecular force, say we have a covalent bond that's polar, maybe even having hydrogen bonding, that would be only 1/10 as strong, and other dipole-dipole interactions being a little less strong even. If you get down to something that has only a temporary dipole, like a London dispersion force, then that would be 1/100th the strength of a covalent bond, or 1/1000th the strength of a macromolecule or a metallic bond, or the ionic bond. Like very, very weak forces overall. Here's what it all comes down to. The weaker intermolecular forces will have lower melting points. Weaker attraction means the substance is more likely to turn into a gas. So here it says it is more volatile. Volatile is the tendency to turn into a gas. So if it has weak forces, there's very little holding it together, less work to do in breaking up the intermolecular forces in order to turn into a gas. You're going to get stronger intermolecular forces when you have larger molecule size, as you can get more polarizability to get stronger London dispersion forces. And then, of course, the more polar the substance, the stronger the forces, as you're going to get a stronger difference in partial charges, which is why hydrogen bonding is stronger than other dipole-dipole interactions. And again, the stronger the intermolecular forces are, the harder they are to break, and the higher your melting and boiling points will be. Let's look at a couple of molecules as an example. First, let's look at diamond, which had a covalently bonded structure. It was sp3 hybridized. It is a macromolecule, a giant molecule in this case, and it has a melting point of over 4,000 degrees Celsius. Let's compare that to sodium chloride. Normally you would think of sodium chloride as having a very high melting point. It is a solid at room temperature, and you may remember from the solubility lab that sodium chloride didn't change much. Even when we heated the water all the way up to boiling, it still wasn't very soluble. The melting point of sodium chloride is pretty high at 801 degrees Celsius, but that's still significantly lower than 4,000 degrees Celsius. So as an ionic compound, it does have a high melting point, but you can see how much higher the melting point is for the network covalent bonds when you compare the diamond to the sodium chloride. Let's compare a few organic molecules so we can see how their structure can affect their melting points. So first we have propane, which is all single bonded carbons saturated with hydrogens. This is not a polar molecule, so the only intermolecular force applied here would be a dispersion force, or London dispersion forces, where you only get very temporary dipoles created just from the moving of electrons as they rotate around the atoms. Not a very strong force of attraction, and we see a super low melting point of negative 42.2 degrees Celsius. Next, let's look at ethanol. Notice it's not ethanol, it's not an OH group, it's just a double bonded oxygen here. Happens to have just about coincidentally the same molar mass as the propane, but it is a polar molecule. The oxygen would pull more electrons from the carbon. So we are going to have a dipole-dipole interaction. I do want to comment real quick on a question I get a lot. Why doesn't this molecule have hydrogen bonding? And that's because the polarity is between the carbon and the oxygen, creating a partial positive on the carbon. In order to have hydrogen bonding, you would need a partially positive hydrogen, not a partially positive carbon. So there's not hydrogen bonding because the bond would be between partially positive carbons and partially negative oxygens. So it is just regular dipole-dipole interaction, and so we do see a higher melting point here of 20.8. But then if we look at ethanol, which actually does have an OH group, we would have the partially positive hydrogen in this case and a partially negative oxygen. So you would have hydrogen bonding in the ethanol, having the OH group. Notice also it has a slightly larger molar mass. So this polar molecule with hydrogen bonding, that is the largest, is going to have a much higher melting point of 78.5. Now let's look at a different physical property, solubility. As a general rule of thumb, like dissolves like, meaning polar substances will dissolve other polar substances, whereas to dissolve a nonpolar substance, you would need another nonpolar substance. Typically, polar substances do not dissolve nonpolar substances, or vice versa. A common feature in organic molecules is that one part of the molecule will be polar. We call this the polar head. And then the chain of just normal carbon-hydrogen chain, this same old carbon-carbon-carbon chain, is a non-polar carbon tail. This is actually how soap works. Here's the picture of the molecule of carbon, and so you can see here we have the tail that would be made of non-polar substances, and we have here the polar, this partially negative head. So water we know is polar, and so water would interact with the head of the molecule. We would actually call that head hydrophilic, meaning water-loving, whereas the tail, being non-polar, would not mix well with the water, so it doesn't like water. We call that hydrophobic. So we have a hydrophilic head and a hydrophobic tail. When soap attacks a stain, say a grease stain, it forms something called a micelle. The hydrophobic ends would surround and dissolve the grease stain. Then the hydrophilic heads, or the polar heads, would dissolve in water, since like dissolves like and they're both polar, and that's going to allow the water to carry away the stain out of the clothes. This is also how your phospholipid bilayer works. The hydrophilic head would be able to be by the aqueous environment, but then the non-polar hydrophobic tails would be in the middle. Organic molecules have their own trend in solubility that you should know, and it's all about the tail. The longer the tail, the less soluble it is. So generally speaking, the longer the chain length, then the less soluble the substance is. So here we're looking at what they call a homologous series, meaning it's pretty much the same except for the tail. We've got the hydroxide group at the end, and then we have just varying lengths of chain here with the CH groups. Here's another example of a homologous series, just to make sure you have the idea. It would have the same functional group, in this case no functional group, and then the length of the chain is changing. So when you're looking at the same functional group with the variation in the chain, you have a homologous series. So in order to really establish a boiling point trend, you would want to compare a homologous series so that you know that the only thing changing is the chain length. And here we can see that the boiling point does increase as you increase the number of carbons. Going back to our first homologous series though, the hydroxide group is actually a really good choice for using a solvent. So if we have something like ethanol, where we have both polar and nonpolar ends, you have your hydrogen bonding that can happen, that's going to be really good at dissolving both polar and nonpolar things, or creating something like a micelle, like soap. Let's compare the first four in the homologous series with the hydroxyl group. So here we have methanol, butanol, propanol, and ethanol, and we're being asked to put them in order of decreasing solubility. The most soluble would have the shortest chain, which would be our methanol. Then we would have the next longest chain with 2 carbons, ethanol. Then we would move on to something that had 3 carbons in the chain, or propanol. And finally, the least soluble with the longest chain would be butanol. And oops, I had my greater than signs backwards, apologies. So methanol would have the greatest solubility, then ethanol, then propanol, then butanol. So the decreasing solubility, the least soluble, was the butanol. The last physical property I want to discuss is the ability to conduct electricity. So first, electricity is defined as electrons moving from one atom to another. So the electrons need to be free to flow in order for something to have electrical conductivity. They have to have free moving electrons. Metals are well known to be good conductors because they have delocalized electrons, electrons that can move freely. Graphite is another example of a carbon allotrope that had many delocalized electrons, so it's also going to be a very good conductor. If we are able to get an ionic salt to become a pure liquid, we would call that a molten ionic salt. That's also going to be good at conducting electricity. Keep in mind that the melting points are really high, and this is not saying aqueous, this is saying actually liquid, pure, molten salt. Those would be good conductors, but it does decompose or break down the bonds holding the ionic lattice together. Be careful with this though, because not all network covalent molecules are really good at conducting electricity. For example, diamond has a very fixed position. Everything is very localized. And so without the freedom to flow, it's not going to be a very good electrical conductor because its electrons can't flow. You have to have free moving electrons, which is good in things like metals and molten ionic salt. That concludes Notes E, and actually that concludes all of the notes for Unit 4, Chapter 4 for the IB textbook. So let me know if you have any questions.